Hi, in this video, I'm explaining the math of the Huntington Hill apportionment method, and that is the rounding method that's used in it that's based on the geometric mean. First, quick summary of apportionment. In the apportionment, we're dividing some sort of total, such as total number of seats in Congress, to the various entities, such as to the several states. Well, we do it proportionally to the population of the states, but when we do it like that, it's extremely likely that the proportions come out as decimals, and you cannot have decimals in terms of number of seats in Congress. The number of seats have to be whole numbers. There are many apportionment methods that do it like this. They take the quotas and they round it off, and they see it after rounding, does it add up to the correct total? Or usually it doesn't. So what they do is they adjust the quota. If they add it to a total that's too low, then they adjust the quota to be a little bit higher. And then they round off again, they add again to see if it works again. And if it doesn't work, they try different quotas. And this is usually achieved by adjusting the standard divisor. They keep adjusting the quotas until the total of the round-offs come out to the correct total. So these apportionment methods propose different ways of rounding. Thomas Jefferson proposed rounding down the quotas. John Quincy Adams proposed rounding up the quotas. And Daniel Webster proposed rounding normally, meaning if the decimal part is 0.5 or more, you round it up. And if it's less than 0.5, you round it down. Whereas the Huntington Hill method does something that you probably have not seen before, and that is that it rounds according to the geometric mean. So let's talk about rounding using the geometric mean. What's the geometric mean? In math, when people say arithmetic, they mean add things together. And when they say geometric, they mean multiply them together. So the mean or average that we're used to is technically called an arithmetic mean. And it's defined as taking two numbers, add them together, that's the arithmetic part, and then you divide them by 2. So for example, if you have 3 and 4, then you go 3 plus 4 divide by 2 and you get 3.5. If you get 10 and 20, you go 10 plus 20 divide by 2 is equal to 15. Now the geometric mean, instead of adding, would be multiplying, and then instead of dividing by 2 to take the average, we're going to take the square root, which is the second degree root. And the geometric mean can be generalized to more than one number. So if there are 3 numbers, it would be A times B times C, and then take the cube root of it, etc. But for purposes of Huntington Hill, we only need to work with 2 numbers. So if you have 3 and 4, then the geometric mean of 3 and 4 would be 3 times 4, and take the square root, which is square root of 12, and that's equal to 3.4641, etc. If you have 10 and 20, then you'd go 10 times 20, and then take the square root of that. 10 times 20 is 200, and the square root of 200 is 14.142, etc. So now let's apply that to rounding. Normally, the usual rounding, let's say that you have the number 7.51. You're going to have to decide whether to bring it up to 8 or bring it down to 7. Well, 7.51, the decimal is more than 0.5. 7.5 is here, and the decimal is more than 0.5, so it got rounded up to 8. And the natural question that you should ask is, why 0.5? Why not 0.4 or 0.6? What's so special about 0.5? The answer is because 7.5 is right in the middle of 7 and 8. In other words, it's because it's the arithmetic mean of 7 and 8. I mean, how do you find the middle of 2 numbers? You add them and you divide by 2. This is the arithmetic mean. Another way to view the normal rounding method or the usual rounding method is to say you have a choice between 7 and 8. Then what you do is you take the mean, or specifically the arithmetic mean of 7 and 8, which is 7 plus 8 over 2 equals 7.5. And then anything that from 7.5 and up, you round up. And anything that's less than 7.5, you round down. There is this cutoff that says from that point and up, you round up, and less than that point, you round down. And that cutoff is determined by the arithmetic mean. What the Huntington Hill method says is, you know what? Instead of doing the arithmetic mean, why don't we switch it to the geometric mean? The way it was, the cutoff for rounding is equal to the arithmetic mean. What the Huntington Hill method does is that the cutoff is the geometric mean. Again, we have to decide between rounding down to 7 or rounding up to 8. So we're going to pick a cutoff, but instead of just the middle of 7 and 8, the arithmetic mean, we're going to take the geometric mean. And that will be 7 times 8, and then take the square root of that, is 7.4833, etc. A little bit less than 7.5. Everything from this point and above, we round up. Everything less than that point, we round down. It's just like normal, except that the cutoff is at a different place. All right, let's do an example. Suppose that our standard quota comes out to be 1.43. So the usual rounding, and that would be what Webster's apportionment uses, would bring this number down because 1.43 is less than the arithmetic mean of 1.5. So it gets rounded down to 1. For Huntington Hill, we would go slow like this. Step 1 is to take the two integers on both sides of it. Our number is 1.43, so the two integers are 1 and 2. Step 2 is to compute the cutoff, which is equal to the geometric mean. And that is the square root of 1 times 2, which is square root of 2, and that's equal to 1.4142. And step 3 is the decision. If our number, 1.43, is greater than or equal to the cutoff, we round up. If our number, 1.43, is less than the cutoff, we round down. Well, in this case, 1.43 is greater than 1.4142, so it falls under the first category here. We're going to round up to 2. Scroll up a little bit. Before, with Webster's method, we'd be rounding down to 1. But with Huntington Hill's method, we round up to 2. So let's make a table to compare this. If the standard quota is between 0 and 1, then the cutoff using geometric mean, meaning the cutoff under Huntington Hill, is going to be square root of 0 times 1, which is square root of 0. equals 0. Under Huntington Hill, anything between 0 and 1 automatically gets rounded up to 1 because everything is above the cutoff. If the standard quarter is between 1 and 2, then we're looking at square root of 2. And we just did that above. It's 1.4142. If it's between 2 and 3, then we're looking at square root of 2 times 3, which is square root of 6, 2.449. Between 3 and 4, that'll be square root of 12, 3.464. Between 4 and 5, 4 times 5 is 20, be 4.472. One more, between 5 and 6, 5 times 6 is 30, and square root of 30 is 5.477. First thing you can see is that the decimal changes each time, so you do have to calculate each time. Let's compare with the cutoff under Webster, which is the usual. Under Webster, cutoff here is 0.5, 1.5, 2.5, 3.5, 4.5, and 5.5. You can see that there's a gap here between 1.4, 142, and 1.5, where some of these would have rounded down under Webster, but rounded up under Huntington Hill. And there's a gap here as well. All of these has tiny little slice where the standard quarter gets rounded up under Huntington Hill, where it would have gotten rounded down under Webster. And it can be mathematically proven that this is true all the time. There will always be a little gap. There's always a possibility of some state being lucky enough to fall in the gap so that under Webster, it would have been rounded down. But thanks to Huntington Hill, it gets rounded up. And that's good for that state. And that tiny little slice was apparently politically advantageous enough to cause Congress to switch out of Webster's apportionment method and into Huntington Hill's apportionment. I hope that's been helpful. Thanks for watching. Press subscribe for more contents. And bye.